first semester calculus course, we're always talking about the derivative, and we're talking about the instantaneous rate of change, and that's what the derivative models, right? And so oftentimes in a graph, we say that the derivative gives us the slope of the tangent line of the curve. Now, it's confusing sometimes to look at a graph of a function and its derivative and compare the two and see how they're related, and that's what I want to show today. All right, so let's look at this example. We have two curves. We have a cubic polynomial, that's going to be my f of x, and then we have a parabola, which is my derivative, f prime of x. How do these two compare? So notice that your original function from negative infinity all the way up to 1 is increasing. In other words, it's going up. As I move to the right, the graph is going up, which means what about the slopes? If we looked at the slope of the tangent line at any point along that interval, we'll see that we have a positive slope. Okay, so now if I have a positive slope of my tangent line, what does that say about my derivative? It says that the derivative then must be positive. And how does that translate to the graph? Well, notice on the parabola, from negative infinity up to 1, we are above the x-axis, which means that we are positive on that interval. And sometimes students say, well, wait a minute, but the parabola is going down. Okay, but that's not what we're thinking about. For the original function, we're worried about up and down, increasing and decreasing. But for my derivative, I'm thinking positive and negative, above and below the x-axis. So let me say that again. For the original function, you want to think increase, decrease. For the derivative, you want to think above and below. And sometimes it's hard switching gears from one to the next. All right, so now notice between negative 1 and 1, my function, f of x, is doing what? It's going down. It's decreasing. So what does that say about the slope of the tangent lines? We have negative tangent slopes. And you can look at the parabola. All of that is below the x-axis. It's negative between negative 1 and 1. What happens after 1? My function, f of x, is increasing now. From 1 to infinity, it's going up. And so what does that say about my derivative? Well, that means I have positive tangent line slopes, so the derivative is above the x-axis. You see the correlation? When f of x is increasing, f prime is above the x-axis. When f of x is decreasing, f prime is below the x-axis. Now notice what happens at 1 and at negative 1. My original function f of x has these highs and lows. They have a peak and a valley, a max and a min. And at those 2 points, we have tangent lines that are horizontal. Okay, a horizontal tangent line has what kind of slope? It has a 0 slope. So that would mean my derivative has to hit 0 at those 2 locations. And now look at my parabola. The x-intercepts are right at those 2 locations at negative 1 and 1. Now I hope this makes sense, connecting the derivative with the original function in terms of their graphs. I want to go over a couple more examples just to make sure that this concept hits home. Of course, if you have any questions, let me know. Most calculus textbooks have an example like this where we're trying to match functions on one side to the derivatives on the other. And so here we're trying to match these 3 functions, a, b, and c, to their respective derivatives 1, 2, and 3 on this side. Alright, and let's look at part A. So now remember, on the left column, we are thinking increase and decrease. That's what we're trying to think of as the functions going up and down. And on the right-hand column, we're thinking positive and negative, right, above and below the x-axis. Okay, so when I'm looking at this first one, part A, first thing I notice is I hit 0 somewhere here in the middle. So my derivative function has got to hit 0 in the middle. And when I say hit 0, I think about it. This is a slope of 0, right? There's no increase, there's no decrease. There's no increase, there's no decrease. Now I want to look at 1, 2, and 3. That eliminates 2 instantly. So I'm either looking at 1 or 3. Okay, now when I'm back looking at A here, before this spot, I'm going up. So that's an increase. So that means I have a positive slope. That means I'm above the x-axis in the derivative. And on this side, I'm going down, which is a decrease. And so I am below the x-axis in the derivative. And so now if you look at 1 and 3, 1 over here, I am positive. I'm above the x-axis, and I am negative here as well. And I do hit 0 right here in the middle. And the same is true for the third one. Actually, So how do I know which one it is? Well, notice in part A that if I'm coming from negative infinity towards 0, I am increasing, but the further I am away from 0, the smaller that increase is, right? So it's a very slow increase at first and then picks up. And as I'm going out towards positive infinity, my function is decreasing, but it starts decreasing at a slower rate, all right? So as I get closer to positive and negative infinity, my derivatives are closer and closer to 0, which will let me know that that's 1 right here, right? Because I'm approaching 0 on both sides. Whereas this third one, actually I have some sort of asymptote. I'm going up to infinity and negative infinity. All right, so let's look at B part. B part, similar to A, I have a horizontal asymptote right at 0. So I think by process elimination, I know this is 3, but let's try to reason it out. At first, I am going up. So that would mean, so that's an increase. That would mean my derivative is positive. And over here, I'm going down. I have a decrease, so my derivative is negative. All right, but now with this particular one, notice on the right-hand side, as I'm getting closer and closer to this point here, my derivative, if you could zoom in here and see it, my derivative is getting more and more closer to a vertical line, and it's decreasing. So that means that my derivative is going to have actually an asymptote there, and so that would be number 3. I can see here that as I get closer to these endpoints on this half circle, my derivative is getting closer to positive infinity, going out towards the left, and negative infinity as I'm going out towards the right. All right, now in part C, let's look. This is decrease, and then an increase, and then a decrease, and then an increase, and then over here it's just constant. So what happens with my derivative? Well, notice though that not only is it decreasing, it's decreasing like a straight line. And straight lines have constant slope. So that means the derivative here is not only going to be negative, it's going to be a flat line negative. And on the increase, not only is it going to be positive, it's going to be a flat line positive. And then when I finally get over to this side where it's constant, slope at that point is going to be 0. It's a horizontal line. So that is how this is related to 2. Because notice I have constant negative, a constant positive, bouncing back and forth like that. And then when I hit the flat line, I just have a constant 0 slope. Alright, so now finally we need to match these up. We said A was 1, we said B was 3, and we said C was 2. Remember, one last time, increase and decrease on your function, positive and negative on your derivative. You have to learn how to switch gears in your thinking. If you can get the connection between f of x and f prime of x, that really helps drive home the importance of the derivative and the connection of a derivative to the original function. So make sure you go over this. I'd be glad to help, and I hope it makes sense to you. Let me know if you have any questions, and thanks for watching.